Let's continue with our class of foundation engineering. I still on chapter number 1. The next point will be about yielding yield function, different yield function for modeling behavior of soil. So this is the before last point. I think this point also we will do several video on this point. So it's just about laws that are governing the behavior of soil. Okay, common method of modeling yielding behavior of soil. So these are the laws that are used in software to compute the behavior of a soil. Okay, so analytical solution to foundation engineering problem, whether they are numerical or deterministic, must accurately model the stress strain behavior of foundation material. So all this this part of this chapter is about relationship between stress and strain, or if you want, between stress and deformation. So the amount, stress is caused by force, right? And strain is caused by deformation. So it's like saying relationship between force and displacement or deformation. So each soil has the stress you will apply, for example, on clay will not cause the same effect, the same deformation if it was applied on sand, for example. Okay, so the solution to any engineering problem must accurately match with the stress strain behavior of the foundation material. That is the very important point, and that is the core of this video, of this point number 1. Not only this video, but this point number 1. So relationship between stress and strain. Stress, strain, behavior. Okay. Why elastic method? Elastic means like linear method. Elastic method, they work very well with low stress. If the stress is not very high, then elastic method is okay to estimate the relationship between stress and strain. Okay. But when the load is very large load, considerably very high loading, then elastic method becomes maybe not good enough. Okay. In that case, we have to find another method. For example, in low permeability soil like clay, clay, the permeability of clay is very low, and silt also. In this kind of thing, when you load, for example, clay, we have talked about this many times here, I think. When you are loading, when you construct a building, for example, on clay material, clay soil, the water inside the clay will take long time before to escape from the ground. Because, for example, if you take a duster and you put water, if you push on that duster, the water will escape, right? So when you build a building on any structure on clay layer, clay soil, the water inside that clay will take longer time to escape, to get out. If it was sand, that is very fast, quickly it will go out. But for clay, it take longer time. So that's why we will have time dependent consolidation. So the settlement will be depending on the time. Okay. However, if we take, for example, the coarse grained soil like sand or gravel, we have excessive settlement due to this the soil particle rearrangement. Okay, the position of the particle will be like will be like a secondary consolidation, just to because of the sand particle or gravel particle will be the position of between them will change, and the void between them will become smaller and smaller because they will come close to each other, and the rotation, because they are not perfectly smooth or like spheric shape. So in clay we have this. In coarse grain, so sand and gravel, we will have this particle rearrangement problem. So these phenomena cannot be adequately captured by elastic or incremental elastic behavior alone. Okay, this kind of behavior of the soil, the elastic method cannot help us here. That is the problem. So we need sophisticated a constitutive model. Constitutive model means stress strain model. Relationship between the stress and strain. We need very good one, very powerful one to allow us to accurately analyze FM structure. Okay, from small deformation stages to large deformation yielding in ultimate failure. Only linear model is not enough. This model not only makes sure that the strength limit are met, that the first objective is to make sure that the strength limit of the soil, the foundation soil, is met, and also the survivability limit also need to be a target. For example, in a foundation, you may in the project you may have like a limit of 10% of pile diameter or 10% of the foundation as limit of the settlement, you know, in the project as the requirement of serviceability limit. The project may ask you to limitate the settlement, like the settlement of the foundation at a distance or like 10% of the pile diameter, for example. Okay, so for example, if your your foundation is, for example, 30 centimeter, the diameter is 30 centimeter, then your settlement should be around 3, maximum 3. You do uh, like the 30 centimeter, you take multiply by 10 and divide by 100, it will be 3, right? So something like that. Even though, even if the settlement at 3 is not actually failure, but the service limit state is asking you to limitate the settlement at this amount. So we need this kind of model, okay? Model that can allow us to know the ultimate capacity, okay? the strength limit. You should never go above this limit, and the service limit. So popular model include modified camp clay model. Please, when I say model, will you understand what I mean? It is here, constitutive model. It means the relationship between stress and strain. That's all. What is the relationship between stress and strain in case of clay? So there are people who have proposed model relationship for this kind, for different type of soil. Okay, so these two famous model, there are a lot actually, many models exist already, but this modified camp clay model is for clay. It's very famous for clay material, for clay soil. Okay, and this one, cap model also is famous for granular soil, means for sand or gravel. But please remember, there are a lot of models, many models. You know already more column model. I guess you know already that there are a lot of models. So in this program, we will just talk about these two, mainly these two. Okay, but if you you can check in, for example, if you have any software, modeling software, you can check the different model that your software is offering. Okay, but it doesn't matter which model you are using, it will be always about relationship between stress and strain. Or to be make it very simple, it will be about the relationship between force and deformation, because the force is just the result, uh, will result in stress, and the deformation will result in strain. So stress strain relationship of the soil. Okay, so these two model. So in this video, we will start talking about this model first, and maybe next video also will be about this model, but the video following will be about this model. Okay, modified camp clay model. Okay, so anyway, strain component can be related to the corresponding stress. We have talked about this before. Okay, and using the constitutive relation matrix, this equation, we have seen it before in the previous video. Please check. Okay, so you have stress here and you have strain here. This matrix, constitutive relation matrix, this is the matrix that is the that make difference between the model. Okay, all the model are same, have they have same idea, same strategy, showing the relationship between stress and strain. Okay, the difference will be in this matrix, and whether it is 2D or 3D dimension. So if you master this, you can create any software you want. Okay, so however, effective application of any constitutive model depend on how it will fulfill the following experimental tasks. Okay, how the model, the constitutive model, can respect this. Number one is appropriate laboratory testing to determine the specific material parameter needed to execute the theoretical model. So if you have a model, sometimes you need to go to in the lab, for example, to know what is the cohesion of the soil, what is the internal frictional angle, okay, what is the unit weight of the soil material. Okay, you determine this from the lab testing. okay, to get the material parameter first. And this material parameter will be the input parameter for your model, for your calculation. Okay, the input data, you have to know them. This model will not give you any model, no model will give you the parameter. So you go on your construction site, you take soil sample, and you go in the lab and do testing, and you get the soil parameter. The soil parameter will be your input data. Okay, and then also field pilot testing based on maybe scale model or prototype. Okay, the prototype themselves. This is to verify that analytical or numerical prediction for actual field application, and perhaps future calibration, calibrate the analytical model. This means when you do numerical analysis, let's say you want to know bearing capacity of a pile foundation, okay? And you do your numerical model and obtain some result. In an actual project, you have to calibrate your model using result from field testing. That means you go for example, 4 or 5 already built, constructed on the site, on the construction site, the site you want to build nearby. Okay, and you perform loading test on those piles and obtain load settlement curves. Okay, then you compare the load settlement curve from the loading test, obtained from the loading test, with those you obtain from your numerical model, constitutive model. Okay, in that case, maybe it will help you, for example, to change some parameter. That's why we are talking about a calibration. Okay, calibrate the analytical model, something like that. Do you understand? So it means numerical model needs lab testing and sometimes field testing also. You do the lab testing to know. You don't have to do lab testing to have a soil parameter actually. You can do also field testing, for example, CPT test or SPT or any other field testing to obtain the soil parameter. But you need the soil parameter as input data. Okay, so you got the input data. The output now has to be validated sometime with the field testing, field loading test, for example. Okay, because the field, the result from field testing are the actual capacity of the pie. What you have in your PC, in your computer, in your PC, is not really the actual capacity of pi. It's just approximate. However, once you validate the model, the numerical model, with the field test result, then you can make sure that your numerical model is good. And then from from that point, you can continue using only that numerical model, because that numerical model has been validated with the field test result. And from then, you can use only the numerical model. It will help you to save time and money, because if you have to test all the pile that have been constructed, built, it's very expensive. Okay, I hope you understand what I mean. So, as I said, come clay model this time in this video. In the next video also will be about come clay model. Modified come clay model. Okay. Remember all the model same relationship, stress, and strain. Okay, that is the key point you need to remember. So the modified come clay model is based on research performed by these references, this reference and this reference. Okay, so it has been successfully applied in many field applications involving deformation of soft clay. But you need to remember that this is for clay. Okay, the name is even very clear. Clay, in the name there is clay inside. So modified come clay model. And in this theory, isotropic consolidation behavior of clay is approximated by the following relationship. I think you remember when we did one-dimensional consolidation. If you don't remember, I will just bring it back a little bit here to help you remember that we talked about this before, right? So isotropic means like same a consolidation behavior. So this come clay model, it will have three part. The first part is this one, isotropic consolidation of clay, which is this one. Maybe we will do even 3 videos on this come clay model. I don't know. Isotropic consolidation of clay. This is the first part of come clay. Second one is critical state of deformation of clay. The third one is stress-strain relationship for yielding clay. So we will divide this part in 3 parts, sub-part. Stress-strain relationship. This is the last one. So in this video, we will do only this one. Isotropic consolidation of clay. Only this part, okay? To keep this video short. Isotropic consolidation of clay. Okay, let's go. So isotropic consolidation of clay. This is, you remember this apparatus, the one-dimensional consolidation test for clay. I don't remember which video, the number of the video, but we did this before. Going with this to help us know the recompression and compression index. And this is the pre-consolidation stress. I hope you remember. If you don't remember, please go back in the previous video and you can find a lot of explanation about this. And we have several cases when you are in this situation, what will be the behavior, the relationship when you are in this situation, when you are in this situation. Anyway, it is just about the stress and deformation relationship. So here, this axis is about the stress, right? And this is about the void ratio, the E void ratio. This void ratio is directly related to the volume, right? Like if you compress a soil element, the force you are using to compress it generate like result in the stress, then we deform the soil element. This deformed soil element will decrease the volume, right? So somehow this is also a relationship between stress and strain. However, this is just one dimension because if you put soil sample here, if you press it only in this direction, vertical direction, it will not, the deformation is not allowed in the the other direction, horizontal. Okay. So if you remember this, you will remember that if you are here, there is a relationship. If you are here, that's this point. This curve means the soil has already experienced all this type of loadings from here until here. And this point means the maximum load that the soil has experienced so far. When you go above this stress level, then you will observe excessive settlement, excessive consolidation, right? This is normal because here the settlement is very gentle. You see the slope is gentle, very small, because the soil has experienced this type uh, of stress already before in the past. Okay, the maximum is being here, so it will be about this one, but in 3 dimension, or almost like that. Okay, the isotropic consolidation of clay, it will be like this, but in 3 dimension. Okay, so following the terminology applied to this figure, this, do you see it about same, but in 3 dimension? This first line and this second line with second slope. Okay, so we have here V. This is the volume, because now we are not in 1 dimension, we are in 3 dimension. So this is volume, and this is P. You will see it now, but this is related to stress. Okay, so P is the mean normal effective stress. The P here, mean normal effective stress, which is defined by this formula. Mean is average. So in this case, we are supposing that sigma 2 and sigma 3 are same. So that's why we have 2 times sigma 3 here, prime, effective. Okay, so we have to put prime. Sigma 1, I'm not sure if some people don't know what is sigma 1 and sigma 3. When you do a triaxial test, sigma 1, the 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 stress, the three stress in the 3 direction, the main, these are main principal stress. Okay, so you add all of them, sum of them divided by 3. This is the P here. Okay, so sigma 1, sigma 3 are the major and minor principal effective stress. Okay, and specific volume V, this V here, you see how the V is related to the void ratio. In 3 dimension, we will do 1 plus E. This is the volume, 1 plus the void ratio, 1 plus E, instead of saying in the previous 1 dimension, we have only E. See? So the standard equation of the normal consolidation line, this normal consolidation is this one. Normal consolidation. This line. This is the recompression line. And this is the compression line. Exactly like in the 1 dimension. Okay. So for this line, don't forget that we are in 3D, because we have the mean, the average of the stress here, P, and this is the volume. So this line, the equation is given as this. Volume, the volume is function of this N the slope, okay, minus lambda here, ln, because here is a logarithmic scale, not logarithmic, but ln of the mean stress. Okay, it's like in high school when you have to determine the equation of this a line of this line, for example. You know that this equation is something like, and the slope is negative because it is like this. If it was this direction, the slope will be positive. Okay, and for this one, the RCL, the recompression line, in this case, the slope is minus k. So we have here Vk, okay? V is Vk minus k ln of P. So as we can see here also, this line means the soil has experienced all the stress, the mean stress in this case, in this line. But this line this is the limit, okay? PC is here. This is the limit, okay? So these two standard equation, I think these equations are very simple and we already know, because if you know that this point is here, it's easy to determine the equation of this line. This is just high school equation, how to determine equation of a line. Okay, so this VK here, this one, okay, corresponding with to this PC, it is like let's go back. Let me go back a little bit to show you. It is like here, this P, the maximum load that the soil has already experienced, and the corresponding void ratio. Okay, so let's go back. Vk here is the specific volume at the start of the recompression here. N, K, and lambda are the model parameter that can be obtained from laboratory isotropic consolidation. When you do isotropic consolidation in lab, triaxial test, okay, using this triaxial cell, you can obtain this parameter very easily. Okay, so these are function of the result of the lab test, function of the triaxial test. This parameter n, k, and lambda. Okay, this n, this lambda, and this k. I put this here. So during the isotropic consolidation test, the clay sample is compressed under 3D stress condition. Okay, same as like the 1D test I presented before starting this. Okay, so this figure we can also show, we can also see that there are many this type of this line, RCL line. This line, for example, is a possible way. This is another one. We can have many of them. Okay, many of them. And that will form a family of RCLs for different VK value. Okay, VK here, in this case, in this case. So this figure also shows that the VK can be related to the over consolidation ratio. Do you know what is over? Do you remember the over consolidating ratio? The meaning. It is a ratio between two two stress, the maximum stress that the soil has already experienced and the actual stress. Okay. So over consolidation ratio is defined as the ratio of the maximum past effective pressure. So PC this year, this is the maximum past previously that the soil has experienced. Okay. To the current effective pressure. Right now, what is the load that is applied on our soil? So this is the over consolidation ratio. So here is equation between over consolidation ratio and the V is volume. Okay. This equation, hopefully for you, all these equations are what the software, numerical software are using. And we can arrange this in this way. Just this one or this one, it's same. Because over consolidation ratio multiplied by P. This definition is very clear, I think. It means P0. P0 is the current load. If you divide the current load, if you divide the, how to say, uh, the previous load, the previous maximum load, PC, divided by the current load, P0, will give you over consolidation ratio. It means that OCR equal PC divided by PO. Then you can see that PO multiplied by over consolidation ratio will be exactly the PC. So you can replace this one by PC without any problem. That's the only thing from here to here, how we did. Using this equation, this definition here. PC divided by PO equal to over consolidation ratio. That's all. Okay. So it is very important to realize that the deformation behavior of over consolidated clay with a given RCL, RCL is this line, is strictly elastic. So this line is elastic because the soil has experienced the the stress in this level before. So this zone, it is elastic behavior. However, the plastic deformation occurs if the stress path corresponding to a specific loading situation displays the stress volume state of over consolidation. Simple. Okay. In that case, if it means if we go above this point, then maybe we will enter like plastic deformation. It will not be elastic anymore. Here, this zone will be plastic. You understand difference between elastic and plastic? Elastic means you can still recover the deformation. But here, if you enter here, you will not uh, recover all the deformation you will cause. Okay, so it must also notice that we have here alpha and k, right? In this equation, and here the alpha and k, sorry, lambda and k, this one and this one, lambda and k, or here these two. These are corresponding to same as CC and CR in this figure. Okay, consolidation, recompression index and compression index is they are equivalent. This is in one dimension, And this is when we are in 3 dimension. Okay. Yeah. So I think that all for isotropic consolidation of clay. Isotropic, remember, same in 3 dimension, but same stress everywhere. Isotropic. So if you understand, you did understand this, it will be our first step to understand modify CAM clay model. Okay. We have 2 more step. Okay. So that all for today. Mm. Thank you very much for your time and see you soon.